work. Does this work? Do you see my slides?
Yeah.
Yes.
Good. Okay, so this is something I presented in 2019 in Alto at the Pencil Code user meeting. And the idea was quite simple. So the idea was to sort of improve some of the existing 3D plotting routines. And the idea of 3D plotting is relatively straightforward, I would say. So if you use things like ParaView or Visits or Vapor or any of the other packages, free or commercial, so you have your data, then they always allow you some post-processing on the data, like you're calculating b squared. Then you apply filters. And from these filters, the ParaView then generates some geometry, some polygons. They might have color, or they might just have one color. And then it's being rendered. And that's exactly what you see over here. So this is an image using ParaView, where I used, I think it's J squared. And I'm showing you isosurfaces of J squared, like, or B squared, or whatever it was. And that's a geometry generation, right? So it transforms data into geometry. And that's just this is ParaView, just an example of ParaView. And here you see actually a few things. So you see streamlines, you see glyphs or vectors, and you also see some volume rendering here with green and blue. Okay. Can I just check? Do you still see my slides?
Yes.
Okay, good. Because my Zoom sometimes has issues. Okay, so now this is just another picture using Vapor. And one of the things I never really liked about these programs is it's hard to imagine where things are in three-dimensional space. I mean, sure, these are sort of polygons, right? 3D space, we can look around and all that. But if you just look at a still image, I always find it a bit difficult to actually imagine where these streamlines are, for instance. I mean, what is behind, what is in front? That's sometimes a bit hard to distinguish. Now, some of the pros of these programs like ParaView is you can read many data formats, VDK, HT5, and whatever. You can even read geometry data. Like people who do simulations, fluid dynamic simulations with planes, they have their vector fields with the velocity, but they also have the geometry data of the plane. So, which is kind of neat. And they also have like a lot of filters like streamlines, isosurfaces, volume rendering, slices, all the stuff you want. But then one of the disadvantages of using these programs is the post-processing is very limited and very slow. In ParaView, it's very cumbersome to do any arithmetic on your data. You can do b squared, that's easy, but anything more than that, it becomes very difficult to do and very cumbersome. Animations is a pain in ParaView. Things look very unrealistic. Like this one doesn't really look like anything realistic. And light and shadow options are very limited. And that's very important because light and shadows, that's what gives it a more realistic look. It also helps you understanding where things are in three-dimensional space. And just as an example, if you look at a picture like this one, it's just some morning light. And here we can already see some features of what makes things look realistic and also what makes things, how we process things in our brain. Right, so first of all, we have like very general light that touches every surface in this picture. But we also have sort of direct light from the sun, which we see clearly reflected here. We also see not sharp, non-sharp shadows, which help us understand where things are in 3D space. Like for instance, this shadow comes from the jar over here. And by looking at the sharpness of the shadow, we can understand how far this jar is from the bread. For instance, here the butter is very close to the plate. And you see we have a very sharp shadow. So this is just one of the things that help us understanding where things are in 3D space. And that's just the natural way our brain works. So looking at these pictures, I mean, that's not how our brain works. So we cannot really tell where things are because things are too uniformly illuminated. Shadows are very poor. So it's really hard for our brain to understand what's happening. But if we have like a picture like this, which is actually very complex if you think about it. You know, all the lights and shadows is actually very complex. But that's exactly how our brain processes images, how we understand where things are. You also see that there's some camera. So there's some focus on here, but it's not very in focus what's in the back. And also what's in the front is also not very in focus. So we know this bread is in the front, this bread is in the back. You know, one of the few things that help us understanding where things are. I just saw some more examples. And by the way, this picture is not a photograph. It's made in Blender, 3D modeling software. So this is a ray tracing image, computer generated, entirely computer generated. And then we also have other things like, you know, surfaces help us understanding where things are. Like here we have a very diffuse surface, the wood, and a very glossy one, the frosting of a donut. And then of course I can do all kinds of things with materials like refraction, so how light goes through the material, how things are reflected, you know, diffuse reflection, direct reflection. Use some scatterings, and you can use all kinds of different materials to make things look a little bit more realistic. And now, of course, these programs like Blender and also the more commercial ones, they have the advantage that you know, you can make really great images to look very realistic. You have a lot of shaders, materials, ray tracing options, and animations are actually very easy to do in those. So if you have like sort of a camera movements, there's some text coming in, and then there's some animation. You can combine it very easily, and that's very easy to do. In Power, for instance, I did it like several times, as it's a huge pain to do that. But then, of course, those are not made for looking at data. Those are made for animations, you know, movies, videos. So there's no data import. There are no filters on data. There's no post-processing, obviously, because you're not supposed to use them on data. So the idea was to actually use something like Blender, one of these 3D software packages, to visualize data. And that's something people have done in the past already. So if you look at this group, I think they are in Pisa, this group, and they visualize sort of molecules like these ones. And there's even a book about visualization in Blender, which I do not recommend at all. It's probably an example how not to write any books. But it talks a little bit about how to use Blender for using visualization. And the only place where I actually found Blender used for scientific visualization is basically biology and biochemistry. And here are just some examples of Blender used in visualization. And of course, they can do it because biology, medicine, all that, they have a ton of money. They have much bigger budgets than we do. So they can actually afford to hire people who just do that. You know, experts on 3D visualization who studied IT. So they can just employ them, and you know, they just make these visualizations. Or they have the money to hire to get other people to do that, right? External companies and all that. So that's, I think, why it's only been used like in biochemistry and medicine. It's just another example here of visualization of using Blender. And the only place where it was not biology or medicine was this place in Texas, I think in University of Texas, where they had like these fluid simulations around the truck, and then they asked the IT department to do these visualizations, and I think they look really nice, and it's you can really see exactly where the streamlines are also in relation to the truck, and also looks relatively realistic. I think they should have improved the colors a bit of the streamlines, but otherwise it looks very nice and realistic. And of course I could do that because I had connections with the IT department. You know, they just had a collaboration. They told them, we want to visualize this. We have the data. What can you do? And the IT department had the experts to put a lot of work into that. Here's just another example. Here you also see the focus of the camera, right? So the back is focused, the front is not. So it helps you visualizing where things are in 3D space. Okay, so now this is all in good. And it shows that you can actually use Blender for data visualization, but the thing is that it's very cumbersome because it's not meant to be used for visualization. So you really have to do a lot by hand. And just to give you an idea how by hand you have to do it, imagine you want to plot a, like a sine function in a simple plot, but you don't have a plot function. What you have to do as well, you would just program a loop to go through all the points on the sine function, and then by hand you have to plot every single pixel, right, on the screen. And on top of that, you also have to plot the axes labeled as pixels. Imagine you had to do that for every plot. Writing a routine, so say a loop that goes through all the points on the sine function, and for all the points it plots a pixel on your screen. And then you also have to do it for the axes and all that, and all those are pixels. It's actually, that's sort of the very atomistic approach that you have to take when you're using Blender, and that's what people do here. And all these things that I've showed you, like this one, they basically take this very atomistic approach, right? So in this case, for example, I mean, they probably have a data set of all these points of the atoms, and then they know, okay, wherever there's carbon, there's a loop of all the carbons, create a sphere, and give the sphere like a dark gray color, and that's the approach to take. So the idea was then, okay, so to make it easier, right? So we don't want to plot our sine function by programming a loop that goes over all the points and plots a pixel. What I want is a very simple plot function, plot sine of x. One line, a single line, not a huge script. And if you look at Blender, but also some of the commercial packages, they all have Python running in the background. So whatever you do here in Blender, creating geometry, animations, materials, textures, colors, lights, cameras, and the movement of all that, and also the change of all that, that can be done using Python as well. And it's actually not too difficult. And then I looked, okay, why haven't people used that, Python interface in Blender to do simple visualization? And I only found like 2 places where people did that. So one is this example here. So it's a mini library for plotting, and it basically just have like 2 or 3 very simple plotting routines. But it's a mini library that hasn't been updated in several years. So you can find it on GitHub. It hasn't been updated in many years. And this person actually who did that, I mean, it's still active using Blender, but it's doing something different. I think some more like architecture visualization in Blender. And the other person was actually an astrophysicist in the US who used Blender for visualization, also wrote a library for plotting things. But again, very specialized, I found, not very general plotting routines. And again, it hasn't been updated in 4 or 5 years or so. It was a bit of, yeah, it's a bit of a shame, but of course, in both of these cases, it's just one person and there's something in the past, and then they had to do something different, right? So it wasn't really a big library. So the idea was then, okay, well, let's write a library written in Python for Blender for visualization. And that's basically what I did with a colleague who's now in Grenoble. And we basically wrote this this library for plotting in Blender. And here it's just an example. So you have Blender sort of interface. You see sort of the 3D stuff here. And down on the top bottom right, you see the Python interface. So we can just put in all kinds of commands and do some plotting. And that's something I used in the past to plot, for instance, Streamline. So we have like half a dozen, or actually more than half a dozen, of plotting routines. And basically the typical ones that you want to have in 3D visualization, isosurfaces, streamlines, simple 1D plot, meshes. What else do we have? Glyphs, so arrows. So we had different kinds of plots. And maybe I could just show you, maybe in just 5 minutes, some example. Just stop sharing this one. Actually, we're actually writing up something on that. And I can just show you very quickly some examples of plots that we have implemented. So that's something I didn't have yet at our meeting where I did this presentation, but we have that in the meantime. So just to give you a few examples of things that it can plot relatively easily, you know, sort of these line plots. So this is not a streamline, strictly speaking, it's just a line plot, sort of this kind of plot, surfaces, arrows, isosurfaces, and streamlines, like down here. And then of course, because Blender is a 3D visualization tool, you know, the resulting plots are usually of pretty good quality. And then you get something like this, you know, adding the right amount of lights and cameras, you get something like this. Just to give you an example, so maybe one of the simple examples. Okay, the streamline plots. Okay, so this one here. Okay, so how does that look like? So I told you before that people who use Blender in the past for data visualization, they had to go through all these atomistic things. But now, because we have this library, all of that is done in the background. So you don't have to tell it, you know, go to this point and, you know, go to this point and create a cube with this size and this color. And then go to this point, create another cube with this color and this size, and so on. Now it's all done, you know, by just using one single command. You know, you go to data, position of your points, you say plot, and it plots it. Single line. And this is actually a slightly more complex example. This is the streamlines down here. So it's this one here. So it's actually a 3D vector field. And this is all you have to do. This is creating the data, you know, just as an example data with the vector field u, v, and w. And then I can also specify some seeds for the streamlines. And then it's just the command, you know, it's basically just a single, essentially a single line. I mean, it's split in multiple lines for clarity, but, you know, it's just a single command with all kinds of options, all kinds of parameters. Yeah, that's that. And maybe just in the last 2 minutes, I can show you an example that I'm just doing at the moment. Actually, I just did it yesterday. So we have these new simulations with twisted magnetic knots. And I can just show it to you very quickly. Any questions in the meantime?
Yeah, so I had one small question. So is this like is this anyway faster than, for example, using ParaView?
Well, it's not fast. I would actually say it's slower, but I mean it's slow in the sense that the visualization is slower. So there's actually some design differences between ParaView and this one. So if you look at say IDL, MATLAB, Python, what you have is these very simple elementary plotting routines. You'd say plot sine of x and then plot your sine of x, plot a streamline in 2D and a plot your streamline in 2D. While ParaView has sort of a different approach, has this filter approach. So you have your data, you apply a filter to that, you know, a slice or streamlines and all that. And there's actually I'm only aware of one library that combines both, which is called MayaV, or actually Maya V2, which is also in Python. And you have these plotting routines like, you know, like in IDL, just say PLD or just say plot data and it plots your data in 3D, which is very nice. But it also has this filter approach. So it has a GUI and then you can apply filters on your data, very much like ParaView. So, so our intention was to have something elementary like, you know, like Python IDL, where you just type in very simple plotting functions. And then if you have something complex, you can just combine these simple plotting functions. But then we also wanted to be able to work on just NumPy arrays, you know, just arrays that exist. You know, very much like when you plot something in IDL or Python or MATLAB or Mathematica or whatever. So you still have to type. So there's no GUI here, right? Although we thought of making a GUI, but that's a lot of work. So you still have to type. You import you load your data, and then you plot your data. And then when it comes to visualization, now we like to have high quality images. And for that, you have to do ray tracing, not just simple rendering like ParaView or Vapor, but proper ray tracing. And if you want to have really high quality images, you put in a few lights here and there. You make sure that everything is fine. And then if you want to ray trace it at a very high quality, it might even take a few minutes for a single image. But you can see immediately the results by not ray tracing it, right? So it's just a simple rendering like you see in ParaView. I mean, that's immediate, right? It just appears immediately. And I can actually show you in this example here. So here we actually have, so this is actually pencil code data. So do you see this code here? Yeah. Yes. Okay, so this is just Python, right? So what I'm doing here is just I import the pencil code library, but also import our library, BlenDaViz it's called, which I call BLT. Okay, and what I do then is, well, I just read the bar file, right? pc.read.bar. And then I use this one single command to plot some streamlines. Okay, that's just one command. And then I have like a whole load of options, right? Which, helps me to improve my plot and also helps to extract exactly what I want to extract from this. And here I just actually want to follow a single field line in this particular example. And I could just copy and paste that into ParaView, and I'm just showing that to you real quick. So let's see, I got ParaView open in this screen. Sorry, I've got Blender open. Do you see Blender? Do you see Blender? Yes. Okay, good. Okay, now you see Blender. Okay, now what I have here is just a very simple scene. Right, so Blender's got this very nice GUI. Now what I have is just an empty scene that you can see here in 3D with just a camera. And here I got my Python terminal. I can do all kinds of stuff. I could do import pencil as PC. And I could use all the pencil commands, right? And what I'm doing now is that I'm just executing the script that you just saw. This Python, I mean, I could just maybe I can just copy and paste it so you can see it directly. I can just copy and paste this like this. Okay. And there's computing streamlines, and streamlines are always they always take a little while. If you don't optimize them, they might take a little while to actually compute. Okay, so now it's past the reading of var file, which also takes a little while. And now you see in this preview, you see my streamlines, right? Do you see that?
Yes.
Yeah, so these gray streamlines. Okay, so these are my streamlines. So that's what, especially just a single command. And then, just like ParaView, you can have a look around and all that. And you can modify things and all that. Now, of course, if you want some more higher quality, actually, this one has colors, which I haven't shown you. Sorry, is there a question?
Yeah, so these are individual lines. The big streamline is consisting of, so there's difference there, right? So you could actually see internal twist easily, right?
Yes, exactly.
Okay, right.
Yeah, you're right. But this is one single line. Okay, so now this is just some preview, very much the same quality as, say, ParaView, just a quick preview. But of course, you can do all kinds of rendering, which takes into account lights and all that. And if I do that correctly, I want a high quality renderer, a ray tracer. And of course, this takes a little while to compute. You can see when I move it around, you can see it's a bit grainy when I move it. It's because every time I move it, it has to ray trace things. But even though it's ray tracing, I mean, for the simple example, it's relatively quick. And yeah, that's basically it. And then you have our ray traced image over here, which you can improve slightly by putting, you know, some background surfaces by hand, which is actually quite easy to do. And then you can do that. And then you get these images that I showed you before in this example.
So, Simon, would it be possible